now. Okay. So as we saw in our pre-class video, a series is similar to a sequence, but not exactly the same thing as a sequence. Specifically, a series is a way to imagine and to understand infinite addition, right? So a series, so this sort of classic notation, and just sort of remind you what that looked like. We use this, this sigma for a sum. A series is an infinite summation, so it's a sum from a starting point, let's say n equals 1, up to infinity, it just keeps going, of these elements of the term a sub n, right? So every a sub n is a number, and what we're doing is we're adding them all up. And I'll sort of point out that this is different than a sequence, which we spent the last couple classes talking about, in which a sequence was simply this infinite list of numbers, right? The a sub n itself. So here we're thinking about this infinite list of numbers, but instead of just looking at the list, we're thinking about adding them all up. And one of the things that we had to wrestle with immediately was, what does that even mean? How can we add up an infinite list of numbers? Does it even make sense? And the answer we saw was generally no, right? It usually doesn't make sense. So sometimes a formal series like this, it's an object that doesn't really make sense and that we can't really draw any conclusion from meaningfully. And the example that we saw, well, we saw a few examples, but an example that we saw that's near and dear to my heart is the one that's 1, like it's like +1, -1, +1, -1, +1, -1, ... right? So this was our sum, or this was our series of the form, the sum as n goes from, let's say as n goes from 2 to infinity, start at a nice even number. The sum as n goes from 2 to infinity, and then our numbers, our a sub n, were of the form -1 to the n. So that's just alternating +1, -1, +1, -1, +1, -1. It's a sequence that makes sense, but when we go to turn this into a series and to add these all up, we saw that this has no answer, I guess, or that it has no way to be interpreted, right? Has no meaningful interpretation / answer. And the reason was because this, this series didn't actually converge to anything. So our most important thing that we learned in the video was a way to interpret what it meant for this sequence, or I'm sorry, this series to converge to a answer, to converge to a limit. And specifically, we looked at the sequence of partial sums. And the sequence of partial sums, we could call this S sub n, right, is our sequence of partial sums. And our sequence of partial sums was specifically of the form in which S sub n was equal to the first n elements of our series all summed together. I'm going to be a little careful with notation here. Let's say the sum as j goes from 1 to n. So I'm not double dipping with the letter n. The sum as j goes from 1 to n of a sub j. Right, so again, our series is this object over here. I'll rewrite it using the j notation. The sum is j goes from 1 to infinity of a sub j. This was our infinite series, adding up infinitely many numbers. But the sequence of partial sums scaled it back and just said, what if we add up not infinitely many numbers, but the first n numbers, right? And we do that for all of these different steps n. So we have this now, this relationship in which S sub 1, right? That was the sum of the first one element of the series. So that's just going to be a sub 1. S sub 2, the second partial sum, was just a1 plus a2. S3, the third partial sum, was a1 plus a2 plus a3. and so on, right? So you could imagine A sub 17 would be the sum of the first 17 elements of the sequence. S sub 100 would be the sum of the first 100 elements of the sequence. And then what we can consider, right, is we could consider the sequence of partial sums. So the sequence S sub n of partial sums, right, that's our infinite list S1, S2, S3, S4, and so on. And we could see whether or not that sequence converged. And what we said is that the series converges, right? So we said, or we say, the series converges if and only if the sequence of partial sums converges. And that was our big insight here. We took this slightly nebulous thing, series convergence, the convergence of series, and we turned it into something that we better understood, this sequence convergence, right? Sequence convergence, that's material that we talked about on Friday, material that we talked about on Wednesday of last week. That's material that we understand a little bit better, while at the same time, I should say that lets us cast series convergence as something that we already understand. So right away, we see why this series over here has no meaningful interpretation and why we cannot conclude anything about it. If we look at its sequence of partial sums, and again, we did this in the video, so I'll just mention it briefly. We could say that the first sequence of partial sums, the sequence of one partial sum, that was just equal to 1. S sub 2, the first 2, right? That's +1 -1, so that's going to be 0. S sub 3 would be +1 -1 +1, so that's 1 again. S sub 4 would be +1 -1 +1 -1. And this pattern just repeats forever, right? So this sequence of partial sums bounce back and forth between 1 and 0. And then what we see here is that this sequence of partial sums does not converge. And so we end up with a formal looking series, right? Namely, this series right here, a formal looking series that has no meaningful interpretation because it doesn't actually converge to an answer because its sequence of partial sums does not converge as a sequence. So, series are really challenging to interpret, in part because a lot of the time we struggle to understand whether or not they actually converge. So we can very easily fall into this trap where we have something that looks meaningful, that looks real. It sort of formally looks like a series. It has this structure, and yet it has no meaningful interpretation because it doesn't actually converge to anything. And much of our work in the near short term will be in trying to understand these things, both formally, how can we manipulate these series formally, and then also practically, how can we tell whether or not a series converges to even determine whether it makes any meaningful sense. And those are going to be sort of our two big thrusts over the next week or maybe a little bit more than a week. So this is a lot of what we talked about last time. Let me pause and check to see if there are any questions at this time. Any questions? All right. Okay. If everybody's doing okay, let's get into some new material then. The first, and maybe I should say, we're going to start right away by introducing a property of these things, a formal property of these things, as well as a type of sequence that we can tell converges. First, let's start with the property. The property that I want to talk about is so-called linearity. So the linearity of infinite series. It turns out, maybe not surprising, that the linearity of our sequences, which we talked about last week, immediately leads us to be able to conclude that there is a certain linearity of series. Specifically, series can break up across addition and can break up against scalar multiplication. That's multiplication by a constant number, like the C here, in the way that we would expect. So let's take a look at this, right? We simply have here the sum, the sum as k goes from 1 to infinity of a sub k plus b sub k. That breaks up nicely into two different sums. The sum as k goes from 1 to infinity of a sub k plus the sum as k goes from 1 to infinity of b sub k. Similarly, if we have a series that is just a constant c times a sub k, right? So here, notice, let's pay attention to these sort of secret parentheses here. This is a series in which the things we're adding up are things of the form c times a sub k. This should end up equaling c times the sum as k goes from 1 to infinity of a sub k. So these are our formal looking rules, right? Basically saying we can break things up across addition, and we can also break things up across multiplication by a constant number. I want to point out that these should feel a little bit intuitive in the sense that what we have up here at the top is just nothing more than breaking up across addition. This is just, or this is loosely similar to rearranging across addition. Right? And formally is not the right word. Intuitively, the opposite of formal, casually, we can see this as originally, right? Because of these parentheses, we had A1 plus B1 plus A2 plus B2 plus ... right? So that's when we're plugging in k equals 1, then k equals 2, and then so on. And that is just equal to, we're claiming A1 plus A2 plus ... Right? So that's the sum of the AKs plus the sum of the BKs. So plus B1 plus B2 plus ... So casually, this feels like we're just taking our series and rearranging it so that we're adding up all the A's first and then also all the B's first. I say casually and not formally because as soon as we start introducing things like infinity, this becomes somewhat problematic, right? Or it has the potential to become problematic. If we have a finite sum, we can add up those numbers in any order we see fit. But if we have an infinite list, it becomes less clear, at least less clear to me, that we can arrange these so that we're adding up sort of like this infinitely many A's first and then this infinitely many B's first. And so a moral or a thing to be concerned about is, as always, when we deal with infinity, things get weird. So we always have to be a little careful. Similarly, for the C's, what we have here is that we have C times the sum. That is going to end up being, again, this is like factoring out a constant. This is something that we're very comfortable with when we have a finite sum of numbers, but something that we should be less comfortable with when we're dealing with an infinite set of numbers, right? So again, that would be on the left-hand side, it's like C times A sub 1 plus C times A sub 2 plus C times A sub 3 plus ... And then what we're doing on the right-hand side is we're simply factoring out that c so that it becomes c times the sum a sub 1 plus a sub 2 plus dot, dot, dot. So both of these things feel like they should be correct, right? They feel like they should intuitively hold true. They hold true in the finite case. They hold true in the finite case. They hold true in the finite case. We want to be careful in the infinite case because things involving infinity have the potential to get weird. In this case, it turns out they are okay. We have this linearity. I'm going to scroll away from whatever nonsense is happening over there. Scroll down here. So that is an important initial property of these series. I also want to introduce a special kind of series, right? So we have our two questions. What are some general properties for all series? Can we come up with specific series that we know converge, or can we come up with strategies for which these might converge? So I want to introduce a specific kind of series that converges, and this is something called a geometric series. So a geometric series is a series of the form in which it starts with a number, a, and then every subsequent term is going to have a constant multiple factor, r, that gets multiplied to it. So as we go from one term to the next, we're adding on an extra factor of r. So this is sort of a general formula for these. So a plus a times r plus a times r squared plus a times r cubed plus dot, dot, dot. Formally, we can write this as the sum as k goes from 1 to infinity of a times r to the k minus 1. And what makes this so-called geometric is that as we go from one term to the next, it's simply getting multiplied by r. So there's this constant sort of increase of being multiplied by r to get from each term to the next. So I'm going to claim that geometric series are one of our most understood series in the sense that we can always tell just by looking at it whether or not the series converges to something meaningful or fails to converge to something meaningful. And this will be the first of our so-called convergence tests. And it turns out that the formula is really nice and straightforward and kind of fun. But to really introduce it, we have to understand, if we're trying to figure out whether or not a geometric series converges, we need to understand what the sequence of partial sums looks like. So let's go ahead and introduce the sequence of partial sums here. So the sequence of partial sums, again, that's going to be a plus a times r plus a times r squared plus dot, 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 up to a times r to the n minus 1. Now, I'm going to do two things here. First, I'm going to factor out the a so that I can just write this as a times 1 plus r squared plus dot, 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 up to r to the n minus 1. And secondly, my favorite step, I'm going to rewrite the entire thing in the parentheses as a times, and now this will become a 1 minus r to the n divided by 1 minus r. Now that step should not feel intuitive. In fact, it doesn't feel intuitive to me, but we can check. Let's check with a small n just to verify, right? So we have this question, does this expression actually equal this expression here, right? So are these things actually equal to each other? And I'm going to claim yes. If we're clever, we can make this following observation, right? So notice, I'll do a small thing. Let's say n is equal to 3 or 4 or something. So if we have 1 plus r squared plus r cubed, and we multiply that by 1 minus r, so this is maybe checking, right? So if we multiply 1 plus r squared plus r cubed times 1 minus r, that's going to equal, well, I'm going to have to multiply this 1 by everything, right? So that's 1 plus r squared plus r cubed. That's what I get when I multiply the 1 into everything. And then I have to multiply the negative r into everything. When I multiply the negative r into everything, I'm going to get minus r, right? That's the negative r times the 1. So that's minus r squared minus r cubed minus r to the 4th, where that last one is from the negative r times the r cubed. So I have to distribute all of this, and what we notice is that the r's cancel, the r squareds cancel, the r cubes cancel, and what's left is just 1 minus r to the 4th. In other words, this long polynomial times this 1 minus r term is equal to the 1 minus r to the 4th term. And then we can simply divide the 1 minus r underneath the 1 minus r to the 4th to get the equivalent of this formula over here. So this formula will hold for any n value, right? Here I did up to r cubed, but it can really be up to r to the anything. And what we'll see is that this sum, this partial sum, will equal this thing down here. Okay, so let's take a step back. What was the point of this, right? Why were we trying to do this? If we zoom out, it's like, oh yeah, we were trying to figure out a nice formula for S sub n, the nth partial sum of this geometric series. So what is the total limit of the series? Does the series converge or not? Well, the series is meant to be thought of as a limit of these partial sums. The series will converge if the limit of partial sums converges. So I'll say that this converges if the limit as n goes to infinity of S sub n converges. But that object, right, the limit as s goes to infinity, of n goes to infinity of S sub n, that is just equal to the limit as n goes to infinity of the formula we just derived up here, right? So that's a times 1 minus r to the n divided by 1 minus r. And we realize that this thing will converge or diverge depending entirely on this piece right here, right? The r to the n. Everything else is just some constant number. A is whatever that first term was. R is that constant ratio in our geometric series. The only thing that's changing is this n value. So as n goes to infinity, what happens to r to the n? And we realize it depends entirely on what r is equal to. As n goes to infinity, if r is really small, this piece will go to 0, and the series will converge. So we end up with this result that says if that r value is small, and here we'll actually quantify, if the r value is less than 1, then r to the n will just shrink down to 0, right? As n gets bigger and bigger and bigger, you're taking a tiny fraction, raising it to a big power. It's becoming even smaller. And so r to the n goes to 0, and our limit of partial sums, aka our series, converges to a times 1 minus 0 divided by 1 minus r. So we get a nice explicit formula for this quantity. At the same time, if our r value is too big, and here we'll say if r in absolute value terms is bigger than or equal to 1, then this limit of partial sums does not exist, right? The r to the n does not converge to anything, and therefore the limit of partial sums doesn't converge to anything. And so the limit as n goes to infinity of s sub n does not exist. And this would be an example of a series that only looks real in a formal sense, but doesn't actually have any meaningful interpretation. It wouldn't actually converge to anything. So let's take this out for a test drive, right? In the video, we talked about the following series, which I then skipped over when we were talking through all of this. Let's take a look at this series right here. The sum as n goes from 1 to infinity of 1/2 raised to the n power. So we saw in the video that the sequence of partial sums, right? We had s sub 1 was equal to 1/2, s sub 2 was equal to 1/2 plus 1/4, so that was equal to 3/4. S sub 3 was equal to 1/2 plus 1/4 plus 1/8, so that was equal to 7/8. And it looks like that it was converging to 1. Right? 1/2, 3/4, 7/8. This seems like it's converging to 1. What we can see now is that if we look at this as a series in which the first term is 1/2, and it looks like this, right? So when n is equal to 1, this is 1/2. When n is equal to 2, this is equal to 1/2 squared, so 1/4. When n is equal to 3, it's 1/8. And we realize that this is nothing more than a geometric series in which each of these terms has an extra factor of 1/2 as we go from one to the next. In other words, this is a geometric series in which the a value, that initial value, is equal to 1/2, and the r value, the constant factor going from one step to the next, is also equal to 1/2. So from our previous work, and based on our formula, from below, I guess, because we're doubling back here, based on our formula from below, this series does in fact converge and it converges to the expression a over 1 minus r based on the formula, and in this case that is just 1/2 divided by 1 minus 1/2, which is just 1/2 divided by 1/2. So this is in fact exactly equal to 1, as we were hoping. All right. So at this point, what questions do you have? What can I address? So the world of series, I guess it sounds like for the moment there aren't any questions. The world of series is sort of a weird one. Because we're dealing with an infinite object, we have to be careful. We have to formally set it up using these limits. And it's not always completely clear what intuitive things from our finite world sort of transcend over to the limit world. So it's a slightly nebulous, slightly unknown world we're currently in, but we have a handful of things we can do, such as using this linearity and understanding that a geometric series might converge or might diverge depending on this value r. The final thing that I want to introduce before we work on some practice problems is the so-called test for divergence. This gives us one final, maybe truism, one final thing that we can realize that will always hold true and will allow us to immediately determine whether or not a series diverges, aka when a series fails to converge. And the test for divergence simply says, I'm going to write it in two different equivalent ways. It says if a series converges, then the individual terms of the series, the a sub n's that make it up, right? The individual a sub n's must converge to 0 as a sequence. Right, so what we have here, we're talking about two different kinds of convergence. We're saying if our series converges as a series, then the individual terms of the series, the a sub n, must converge to 0 when considered as a sequence. And that sort of makes sense, right? If you're adding up infinitely many things and having it converge to some number, we would expect the individual terms we're adding up to get smaller and smaller and smaller, much like 1/2 plus a 4th plus an 8th plus a 16th. Those individual terms are getting smaller and smaller and smaller. So this is one way that we can write this statement, but it doesn't really, maybe I should say if the series thing is called a test for divergence, this doesn't really seem like a test for divergence. The way I've written it here, it seems like it's all about convergence. So here's our equivalent formulation. And here's where you can really see it as a test for divergence. Equivalently, we can write if our a sub n as a sequence does not converge to 0, then the corresponding series, the series of a sub n's, must diverge Yeah, so again, what we have here, let me see, to address that question, if we have our sort of expression, let me zoom further off to the side here. Boop, there we go. So if we have a expression of the form a sub n, but we have this summation out front, right, as let's say n goes from 1 to infinity, this is like an infinite summation a1 plus a2 plus a3 plus dot, dot, dot. The fact that we're adding up all of these terms is making this our series, while the corresponding sequence of terms is just a sub 1, a sub 2, a sub 3, dot, dot, dot. So this is a sequence of terms. And that's not necessarily to be confused with our sequence of partial sums. So we also had the sequence A1 and then A1 plus A2, so the second partial sum, and then A1 plus A2 plus A3, and so on. This was our sequence of partial sums. So we used the sequence of partial sums to determine whether or not a series converged, but the test for divergence is slightly more, I guess, straightforward than that. It is simply looking at the sequence of terms as a sequence, and then the series as a series, and saying that if the top one converges, if the series converges, then the bottom one not only converges, it must converge to 0. And contrapositively, if the bottom one does not converge to 0, then the top one cannot converge. The top one must diverge. So, Caleb, did that answer your question? Cool. Cool. Okay, so this is great. This is giving us some initial tools that we can begin to use to begin exploring the world of infinite series. And in what follows, there are a bunch of practice problems that we can work on both together and individually to try to get a better handle on this. I'm going to keep an eye on the time. We have just under 15 minutes, so I want to maybe hit some highlights from the second set of problems, leaving the rest of them as practice for you to work on and also to fill in on the community hub. So first, what we can do is if we know certain facts about certain sequences, certain facts about certain series, we can extrapolate using the linearity of series to draw more powerful conclusions, right? So let's say, suppose we have two series. We have a series involving a sub n and a series involving b sub n. And we don't necessarily know what these are, but we know that they each converge. The first one converges to 5 and the second one converges to 3. Formally, we can use the linearity of our series to come up with solutions for convergence of new series. So let's look at C, right? Let's just jump right down to C. Here is a new series involving the terms of the original series A sub n and B sub n. The question we can ask is, what does this series converge to? And we can compute this purely formally, right? Just using sort of our formal understanding of linearity. And so what I can do formally is I can rewrite right? I'm just going to rewrite the inside. I'm going to write this as 2 times A sub j plus -1 times B sub j. I'm going to get this. And then by linearity across addition, right? So by linearity across addition, I can split this up into 2 series, one on the left-hand side of the addition and one on the right-hand side. So this can now become the sum as j goes from 1 to infinity of 2 A sub j plus the sum as j goes from 1 to infinity of -1 times B sub j. From there, again using linearity, but this time using that linear fact that lets us pull out constants, right? So the constant pulling out, I can pull out a 2 and I can pull out a -1. And so that will give me 2 times this summation, the sum of the A sub j's, plus -1 times the sum of the B sub j's. Finally, I can actually use the facts that we were given from the beginning, the fact that A sub j was equal to, let's remember what the hell it was equal to. It was equal to 5, and B, the series for all the B's was equal to 3. So I can use those facts from above. This one was equal to 5. This one was equal to 3. It was just given to us in the problem. That's the only way we really know this. But by using information from the problem, this becomes 2 times 5 minus 1 times 3. So we get that this new total series is equal to 7. So on the one hand, it feels like we haven't really done that much in this kind of problem, right? It feels like we've just sort of split things up in a way that feels natural. We've pulled out constants in the way that feels natural, and then we've plugged in and gotten this new answer. And in a way, that's completely true. But again, to underscore the importance of what we've been doing here, series are challenging. We don't always know if the expression we're writing actually means something and can be evaluated as a number. And so what we've done is gone very formally, explicitly using the rules that we're allowed to use and sort of citing them as we went until we were able to arrive at an answer. This should feel similar if you think way, way back to Calc 1. This should feel similar to our original use of the limit laws, in which we were performing computations that we thought were intuitive, but because we were working in this new world of limits, we had to be very careful, very formal, break things up appropriately, break things up appropriately. We're doing sort of the same heavy lifting here. Here we have a bunch of sequences, a bunch of series in which we're trying to determine whether they converge or diverge. And if they converge, we want to calculate what they actually converge to. So again, geometric series are the one and only kind of series at the moment that we have a really good handle on. What we want to do is we want to think through whether, or I should say, we want to think through what the common ratio R is, right? Again, a geometric series is always of the form 1 plus R. I shouldn't say 1 plus R. It's A plus A times R plus a times r squared plus a times r cubed plus dot, dot, dot. And it converges to the formula a divided by 1 minus r if the absolute value of r is less than 1, and it diverges otherwise. Specifically, if r is bigger than or equal to 1. So, if we want to take one of these to examine in closer detail, we could take, let's say b, 4/5 raised to the n power. Well, that's equal to, if we write out the first few terms, right? This is starting at n equals 0. So at n equals 0, this is 4/5 to the 0, so that's just 1. This is 1 plus 4/5 plus, when n is equal to 2, this is 16/25, plus when n is equal to 3, it's 64 1/25, and so on and so on. But we can notice, first of all, that the initial term is just 1. That's going to be our a value. Color here, that's going to be 1. That's our a value. And as we go from one term to the next, we're multiplying by 4/5, and that's going to be our r value. So think about this. What can we conclude here based on our rule? Well, what we get is that because a is equal to 1 and r is equal to 4/5, 4/5 is smaller than the number 1. So according to our rule over here, it's going to converge. And for b, it's going to converge to the a value, which is 1, divided by 1 minus 4/5. AKA 1 over 1/5, AKA 5. So this series, not only will it converge, but it will converge to the number 5. And we can conclude that just by using this geometric formula that we derived. Any questions about that? Right. So I think there are 2 more small things that I want to talk about on this back list. Yeah, problems 3 and 4. So problem 3 is that third thing that we learned about, the test for divergence. How do we know that this series diverges? Right, well, this series, the series as j goes from 1 to infinity of j over 4j plus 1. If I call this a sub j, right, if this is my term, we can just make the explicit observation, note, as j goes to infinity, the individual terms of a sub j, they're getting closer and closer to 1/4. Right, as we plug in bigger and bigger j values, this becomes sort of the dominating piece of the numerator and the denominator. That +1 matters less and less. And so AJ as a series, I'm sorry, AJ as a sequence converges to 1/4. Because that sequence does not converge to 0, our overall series cannot converge. So this means by the test for divergence, that entire expression, the sum of all these a sub j's, just cannot exist. And the reason for that is because if you think about it, the individual terms getting closer and closer to 1/4 means that the individual sort of terms of the series, it sort of becomes like adding plus a fourth, plus a fourth, plus a fourth, plus a fourth, forever and ever. So it clearly must diverge going up towards infinity. So the overall series cannot exist. The very final thing that I want to say, I realize we're basically at time here, and this is just a quick 30-second note. We can make the observation that our formula need not explicitly start at n equals 1 or at n equals 0. Right? In this case, we can make the observation that if we start at n equals m, one thing we can do is we can notice that this is like a times, the very first term on our list is a times r to the m plus a times r to the m plus 1 plus a times r to the m plus 2 plus dot, dot, dot. We can notice that our first term is a times r to the m, and each individual term going from one to the next still has this constant factor of r, so times r times r times r, and so on. And so we can derive a new formula that looks almost the same as the old formula. The only difference is that instead of having just a single a up here, we write the entire first term. So a times r to the m divided by 1 minus r. And so there's this question, if we don't start explicitly at n equals 1, but instead we start somewhere else, what might this be? This will be our starting point. Okay, and that definitely brings us up to time.